In this video, you will learn about the behavior of soils under loads, failure in soils, and important soil properties, along with methods of their determination. When load is applied to the soil, it is carried by two constituents: the water in the pores of the soil, as well as the solid grains. The increase in pressure within the pore water causes drainage, that is, flow of water out of the soil. The amount of drainage depends on the permeability of the soil, and the load transferred to the solid grains. The strength and compressibility of the soil depend on the stresses within the solid granules. These are called effective stresses. The effective stress in soils is given by the difference of total stress on the soil and the pore water pressure. Now, the shear strength of the soil is defined as the magnitude of this effective shear stress that a soil can sustain without experiencing failure. When the shear strength is so less that it becomes equal to the shear stress, it results in failure of the soil, called shear failure. This failure occurs because the stress on the soil becomes equal to the magnitude of stress the soil can sustain. Soil usually fails in shear only. Shear strength is an important parameter, as the safety of the foundation, and consequently, the whole structure, depends on it. A shear failure can cause collapse of the structure. So what exactly happens during shear failure of soils? The soil is comprised of discrete mineral grains, with intergranular liquids and gases engulfed between them. These soil grains slide over each other along a surface called the failure surface. When they slide over each other, the structures in the soil also get displaced and fail. Note that the individual grains do not get crushed during shear failure. They only slide over each other. Let's take a look at the different types of shear failure. The general shear failure is seen in dense and stiff soil. Here the failure surface is continuous, well-defined, and distinct. A continuous bulging of shear mass, adjacent to the footing, is visible in this failure. This effect results in the tilting of the footing. The local shear failure is seen in relatively loose and soft soil. In this case, the failure surface is not well defined, and it doesn't reach the ground surface. A slight bulging of soil around the footing is observed. There is no sudden failure or tilting of the footing, in this case. The punching shear failure is seen in loose and soft soil, and at deeper elevations. There is no particular failure pattern observed. The soil doesn't bulge, but the footing undergoes settlement in this type of failure. Now, you will understand some important soil parameters in the context of foundation design. The downward compressive loads acting on the foundation are transferred from foundation to earth through bearing capacity of soil. The bearing capacity is defined as the ability of soil to safely carry the pressure placed on it. It denotes the capacity of load bearing of the soil without undergoing a shear failure, nor exceeding the prescribed values for settlements. In other words, it is the maximum downward intensity of load, which the soil can resist without failure. Its dimensions are defined as load per unit area, which is analogous to pressure. This bearing capacity of soil is of different types. The ultimate bearing capacity, QU, is defined as the gross or total pressure at the base of the foundation that causes shear failure of the soil. The net ultimate bearing capacity, QNU, is the net increase in soil pressure that causes shear failure. It is given by the difference of the ultimate bearing capacity and the overburden pressure acting on the soil. The net safe bearing capacity, QNS, is defined as the net soil pressure, which can be safely applied to the soil, without failure. Only shear failure is considered in this case. The net safe bearing capacity is given by the ultimate bearing capacity, divided by a factor of safety. The factor of safety is usually taken between 2 to 3. Again, the net safe settlement pressure, QNS, is for the second consideration, that is, limiting the settlement. It is the net soil pressure that the soil can carry, without exceeding allowable settlement. So, while the net safe bearing capacity is for the shear failure, the net safe settlement capacity is for the allowable settlement. The net allowable bearing pressure, QNA, is the lesser of both net safe bearing capacity and net safe settlement pressure. It is the net bearing pressure that can be used for design of foundation, considering both the above conditions: shear failure and allowable settlement. Now, you will see some of the methods incorporated for determining the bearing capacity of the soil. The first one is the presumptive analysis. Based on experience with structures that are already built, building codes of various countries prescribe the allowable bearing capacity. This can be used for proportioning footings, which is called the presumptive analysis. In India, the IS 1904 recommends that, in the absence of soil test data, safe bearing capacity data can be obtained from a given table of presumptive values. There are also different analytical approaches, developed by various geotechnical investigators, which are mentioned below. These analyses are carried out by studying the properties of the soil grains, like cohesion, friction, angle of shearing resistance, internal stresses, etc. Some of the important analytical methods are Prandtl's analysis, Terzaghi's bearing capacity theory, Meyerhoff's bearing capacity theory, Hansen's bearing capacity theory, and the IS code method, in which the IS 6403-1981 gives this equation for the net ultimate bearing capacity. There are some standard geotechnical tests, which are widely carried out in different places, for calculating the bearing capacity. Some of them are the plate bearing test, in which a compressive stress is applied to the soil layer, using rigid plates. The deflections are then measured, for various stress values. The standard penetration test is done on the site, and not in the laboratory. In this test, a tube is driven into the ground by blows from a slide hammer. The number of blows of the hammer, required to penetrate the tube into a certain standard depth, is recorded. The relative capacity of the soil is then indicated based on data from other standard conditions. The centrifuge method is a technique in which modeling of foundation behavior is carried out. Here, physical scale models of soil systems are placed in a centrifuge to check their behavior under simulated conditions. Let us now understand a bit about soil settlement. The allowable settlement is the acceptable amount of settlement of a structure, beyond which it will be considered as failure. Usually, a factor of safety is included in deciding the allowable settlement. The subgrade modulus is a stiffness parameter, typically used in defining the support conditions of footings. Physically, it is defined as the bearing pressure of the foundation on the soil that will produce a unit deflection of the foundation. It is also called soil spring constant. It is obtained by dividing the capacity of the soil by the allowable settlement. Its dimensions are expressed in force per cubic length. This concludes the concepts on mechanics of soil. In the next video, you will learn about the construction of a foundation on site. Thanks for watching.